Okay, so for the chain rule, when we look at our function, we can look at it in two pieces such that we have one function inside of another function. And what we're going to have to do is take the derivative of the outside function without changing the inside. Then we take the derivative of the inside. So that's what this formula says. If I have f of g of x, and I want to take the derivative of that, I take the derivative of f, I leave g of x the same on the inside, then I multiply that by the derivative of g of x, or g prime of x. Okay, we've been doing that. We've been doing that with the general power rule. We've had like x raised to some power, but then the derivative of just x alone is what? This is, let me write it out so we're all on the same page. The derivative of just x is what? 1. Very good. Okay, the derivative of just x is 1, right? So, if I've had, let's say, f of x equals x squared, let's just say x squared, then f prime of x, okay, I kind of deal with the exponent first by bringing it out front, right? And then we didn't have to write it down, but the derivative of x is 1. So we've kind of been doing this already, okay? Let's look at it in a more extensive example. Here we have the general power rule. Earlier we had a simple power rule, which is pretty much what I did over there. But the general power rule says if I have the derivative of u to the n, where u is some function, it's no longer just the simple variable x, then we're going to bring n out front. We're still going to subtract 1 from our exponent, and I have to multiply it by the derivative of the inside, or derivative of u. Okay, so let's see an example. Okay, suppose I had f of x equals 9t plus 2 to the 2/3 power. Then f prime of x is going to equal, I'm going to bring the 2/3 out front. I'm not going to do anything to the inside right now. I'm going to subtract 1 from the exponent. We get what? Minus 1/3. Okay, now I have to take the derivative of the inside. Okay, the derivative of 9t plus 2 is what? 9. So we say times 9. Okay, and now we can simplify. All right, so to simplify, I'm going to cancel the 9 and the 3. Okay, that's going to leave me, the 9 and 3 leaves me with a 3. And so we get 6 over 9t plus 2 to the 1/3 power. Okay, questions about that? As what? A radical, you mean? Yes, we could write that as the cube root of 9t plus 2. Think of this as an inside and an outside. This was our inside function, and then this other piece is our outside function. I don't know which color. This 2/3 is our outside function. So when I did this, okay, that dealt with the derivative of the outside. I left my inside the same. And then I came over here and I took the derivative of the inside function. Okay? And so this is probably the most simple example for a chain rule, but the inside and outside could be anything, and we'll see that a little bit later. But for now, we'll stick with this special case that we call the general power rule. Let's look at second example. Okay, first of all, I'm just going to rewrite this as what? Okay, 12x minus 5 to the 1/3 power. Okay, that was just algebra. Okay, now I'm ready to take my derivative. So I bring my exponent out front and I subtract 1/3 minus 1 is what? Negative 2/3. Okay, now I take the derivative of the inside, and that's just 12. Okay, and so we're ready to simplify from here. So 12 divided by 3 is 4. Okay, we still have 12x minus 5 to the minus 2/3, 4 over 12x minus 5 to the 2/3 power. And that's our final answer. Okay, so this is where it starts to get a little more interesting. Now on the inside we have a what? A quotient, okay? But otherwise the problem is still the same. Okay, on the outside I've got a power, and so when we have that power on the outside, that's what makes it the general power rule. I'm going to deal with the outside first, and then when I deal with the inside, I'm going to use the quotient rule. Okay? So we get h prime of x equals 3. Okay, that's how we would deal with the power, right? Okay, I'm just going to go ahead. The important thing to remember is when I'm dealing with that outside, the inside does not change. Okay, don't take the derivative of the outside and the derivative of the inside and say you're done. That'll be wrong. Okay, so I dealt with my outside, inside stayed the same. Now I've got to use that quotient rule. Okay, so we say times low, so 2x plus 3, derivative of high, which is what? Just 6x, okay, minus high. I'm out of digital ink. There it is. Okay. Derivative of low, which is just 2, all over low squared. Okay, hopefully that is, you were singing that to yourself while we were waiting on the hurricane. Okay, all right, but that's the derivative. The rest of this is for us to simplify. Okay. Questions about what I did before we go on to simplifying? Okay, very good. Okay, so simplifying, I've got 3. I'm going to write this as 3x squared minus 2 squared. I'm going to come back to this numerator over here, but in the bottom, since both of these are 2x plus 3, I can say I have 2x plus 3 to the what? How many did we have over here? 2, and then it's 2 over there, so it's to the what? 4th, right? Okay. And then I don't see where I can do any of my fancy factoring over here, so I just got to jump in. We get 12x squared plus 18x, okay, minus 6x squared, and that's going to be plus 4. Or 3 times 3x squared minus 2 squared. 12x squared minus 6x squared is 6x squared plus 18x plus 4, right? All over 2x plus 3 to the 4th. Okay, questions about that? We can at this point. It really just kind of depends on what the question's asking us to do. You know, so if I had to set this thing equal to 0, then I would need to go ahead and see if I can factor that 6x squared plus 18x plus 4. Okay. All right, questions about this? Okay. Yes. Okay, because there was a second power here, and so this would become on the bottom 2x plus 3 squared. Right. And so we had 2x plus 3 squared on both sides, so it became to the fourth. Okay. Other questions? All right, very good. So that was C. Okay, D. What do you see that we have here? Yeah, we got a product. And then as part of the product, we might have this, we might need to use our general power rule. I'm going to rewrite this as 1/2 times x squared times 16 minus x squared to the 1/2. Okay? So first I'm going to use the product rule. All right, so y prime equals, now that 1/2, since it's a constant multiple, we might just want to pull it all the way over to the side, and just let him go for the ride. Okay, that's probably the best way to handle him. So let's just say 1/2. All right. All right, now here's my first. X squared is going to be my first, and then this is going to be my second. So first times the derivative of the second. Okay, we're going to come back and deal with that in a second. Plus the second times the derivative of the first. Well, the derivative of the first is just what? 2x. Okay. All right, so now I just need to find the derivative of the second. Okay. So the derivative of the second is going to be what? One half, very good. 16 minus x squared to the negative 1/2. What else? Very good. Times negative 2x. Okay, we used that general power rule on the second piece. Okay. And so now I've got two huge terms. At least one of them is pretty large. This is one term, and then this is my second term. Okay, in this first term, I can cancel out this 2 with this 2. Okay, we're left with a negative. And then I'm going to put my x's together. So we get 1/2 negative x cubed, because I have x squared here and negative x here, and then times 16 minus x squared to the negative 1/2. Everybody with me? Okay, plus 16 minus x squared to the positive 1/2 times 2x. I had a negative here. That was, yes. I just went on and brought that negative out up front. We were multiplying. Okay. All right, so now I think I can start to factor out. Okay, what do my terms have in common? I'm going to pull out a negative x. Okay, so we're going to say I'm going to put the negative on my 1/2, x. Okay, what else are we going to pull out? 16 minus x squared to what power? Negative 1/2. We choose the lowest power. Okay, so we pull out the smallest power, the lowest number, and what are we going to have left? I took out an x, so we have x squared left. Okay, I've also taken out 16 minus x squared to the negative 1/2, so I don't have to worry about anything else there. Okay, and then over here, 16 minus x squared to the 1/2, what is that going to become? What we do is, this is when we factor out, it's kind of like dividing by that thing. So if I divide 16 minus x squared to the 1/2 by 16 minus x squared to the negative 1/2, what's my exponent going to be? 1. Wait, is it? Yes, 1. Okay, we subtract. That's the rule. Okay, so we get 16 minus x squared to the first power. Okay, and I still have over here what? A 2. Okay. It's different, but it's really efficient to factor that way, don't you think? I think it is. All right, so we clean this up. We got negative 1/2 x, okay, times, I can go ahead actually and put, I don't have to write this too many times. I'm going to go ahead and put this 16 minus x squared to the negative 1/2 in my denominator. So we got negative x over 16 minus x squared to the 1/2. Okay. My 2 is still in the denominator as well, because it was a 1/2, so there's a 2 there. And then over here we get x squared plus 32 minus 2x squared, or minus x over 2 times 16 minus x squared to the 1/2. Okay, and we get negative x squared plus 32. So we could put, and that's my final answer. Okay, questions about that? Right here, I pulled out a negative x, and so this should have been a minus. Is that what you're saying? Well, yeah, whether we put it on the 2 or up front, because see, these are all multiplied together. So if I took out a negative x, or basically I factored out a negative, so then that would have made this actually minus. So that would change our answer. Okay, so I factored out a negative, so this should have become minus. And so down here we would have had minus 32 plus 2x squared. And so that would be 3x squared, and it would be positive. So positive 3x squared plus 32. Okay. Questions about that? All righty.
Okay, so you changed the signs right there.
Yes. And then this also was a 3 down here. Okay. All right, so, all right, here's some more places where we might use the chain rule. Okay. Why would I use the chain rule here? Well, what's my outside function in A? Sine. Okay. Now let me say this. I saw a little bit of this on the quiz. This is not sine times pi x. This is sine of pi x. Okay, kind of like that one's a little clearer. It's cosine of that thing. So we don't write it that way, but this is just like, f of x. We say sine of x. Okay, sine's a function that we're applying to some argument x, right? So that's why in this case sine is my outside function. My inside is pi x. Okay? So how am I going to find the derivative? Okay, y prime equals cosine pi x. And then what else? Not 0. It's pi. Okay, pi is just a constant, right? So it's like saying 3x. The derivative of 3x is 3. The derivative of pi x is pi. Okay. Can I do anything else with this? No. Okay. This pi x is tied to this cosine. Okay. He's not floating out there just all by himself. So no, I can't do anything. I might write this like this. Okay. But I can't multiply that pi and the pi x together. Okay. Questions about that?
Is there, we're not doing anything, so sine x doesn't get placed into that function?
No, what we did was we took the derivative of sine x, which was cosine, and then when we said cosine, it was at the same inside function. So now we come and we take the derivative of the inside. So if sine was my outside function, this is the derivative of the outside function. All of this is. And then the derivative of the inside function was this piece. So let's go back.
So it's a chain instead of power.
That's right.
Why would we not use power?
We don't have any powers in this one. Okay. Okay, what about B? Okay. Y prime equals, oh. Well, now all of this is on the inside. Okay. If we said, if the function was y equals cosine squared 1 minus 2x, then yeah, I might move that 2 out front first. But in this case, the square is over here.
So it's part of the,
It's on the inside. Okay. The only part that's the outside is just cosine. Okay. So then the derivative of cosine is negative sine. Okay, my inside here is 1 minus 2x squared. Okay. Now I have to take the derivative of the inside. Okay. This is my inside. All of this is my inside. So what am I going to do? Okay, now I can bring down that 2. 2. And this has an inside, right? So I'm going to say 1 minus 2x to the first. And I still have to take the derivative of this inside. Okay, the derivative of 1 minus 2x is what? Negative 2. Questions about that? You don't understand them?
yeah, like why?
Or
The combination of the two,
Okay. Let's see. Is it the minus sign that confuses you?
It's why the exponent isn't being
This exponent?
yeah,
Okay.
been taking the derivative of that.
Because this is different from this. Okay. When I write this, this is the whole thing squared. This is equivalent to saying cosine of 1 minus 2x squared. So the square is on the cosine. It's not on this thing. Okay. This thing is inside of cosine. All right. And so down here, it's the same thing. The 2 is not on the outside. It's on the inside. Okay. If it had been on the cosine, then yes, the first thing I would do would bring that 2 out front. Would be to bring the 2 out front. Okay. Yes.
Can you highlight the inside and outside again?
Sure. This one kind of has lots of insides and outsides. Okay, the outermost part is cosine, and the derivative of that is minus sine. Okay, and we didn't change anything here. Okay, everything over here stayed the same. All right, then the next outside part would be this 2. So I brought him here. His inside part was 1 minus 2x. So we didn't change that. But we did, of course, subtract 1 from our exponent. And then finally, the most inner part here is the 1 minus 2x, and the derivative of that is negative 2. Does that kind of make sense?
It's like we're doing half of a power rule and then the chain rule.
Well, yes. Well, not really half of it. I mean, we used the power rule when we had a power. So I didn't use the power rule here because there was no power on this piece. But when I got here, then I had a power, so that's when I had to use the power rule.
You see the product rule.
You see the product rule?
See the half of a product rule and then the chain rule.
Well, there is no. We'll never use a half of a product rule. Okay, so let's see. Because the product rule is first times the derivative of the second plus the second times the derivative of the first. Uh, so you're saying you see this as your derivative of the second. No?
Oh, yeah, I suppose. None of the trig functions are missing. I'll figure it out.
Okay. Okay. Other questions about this? Yes.
So would you simplify that any further?
Yes. Yes. So at least clean it up a little bit. I've got a 2 here. I've got a negative 2 here. So, and then I've got a negative here. So we can call that 4 sine of 1 minus 2x squared. I can't separate these two. They're tied together. Okay. And then times 1 minus 2x. So just kind of rearranged things, cleaned it up. All right. Questions about that? Where did I get the 4 from? I had 2, 2, and a negative.
Shouldn't it be 8x?
It was a negative up front.
1 minus 8x?
Where?
You're not multiplying the green part out. You're just times the negative 2 by 2.
Right, I didn't multiply the green part out. I had a 2 here, a 2 here. So I said 2 times 2 was 4.
Maybe negative 4 and that would cancel the negatives.
Right, negative times negative 4 gives us a positive 4. Yep. Okay.
So is there any other explanation other than to when you're dealing with this type of trig function? You just take the derivative of whatever it is and then do the chain rule of the function of the u and inside.
Yes, but the thing is like it's all the whole thing is a chain rule. There were just really 3 inside parts, or three parts. Cosine was on the outside, and then, say that again. I don't mind answering. I'm sure somebody. Okay, so there are three parts here. Cosine is on the outside, right? So let me see if I can try to write it this way. This function y was cosine of something. Okay? Okay. All right. Okay. All right. Anybody else want me to go for it, or y'all good? Okay, good. Okay. You're welcome. Okay. Yes, we got really happy with the trigonometry here. All right, let's do one together, and then I'm going to let you do a couple on your own. Okay, let's look at C. Okay, we got g of v equals cosine v over cosecant v. All right. As a reminder, just so that we remember, because it's been a minute. Okay, the derivative, of cosine v, okay, that one we should know very well, is what? Okay, minus sine v. The derivative of cosecant v, okay, I do know it starts with a negative, and I think it's minus cosecant v cotangent v. All right, who's got those notes nearby? Just to make sure we're all on the same page on that. Yes. Okay, good. All right. So that's our reminder of our derivatives. Okay. So I've got a quotient, right? And the reason I'm having to use a chain rule is because within my quotient I have functions whose derivatives I will need to take. Okay. But I think, I don't know, this one's probably pretty simple overall. Okay. G prime of v, I'm using the quotient rule, is going to be low derivative of high. That's going to be minus sine v minus high derivative of low. Okay, I'm going to need some more space. So let's see. So there's going to be negative cosecant v times cotangent v all over low squared. Notice how I wrote the denominator squared. It was the whole thing squared, so the square goes on the cosecant. Okay. All right, so that's the derivative. We didn't really use the chain rule here. If the v had been, let's say, 2v, then when I did the minus sine v, I would have to say, or rather minus sine 2v, I'd have to come in and take the derivative of 2v. Okay, but we didn't have that, so whatever. Okay, so we're going to try to clean this up a little bit. What can I do up top? How many terms do I have? Okay, we can factor out cosecant. Okay, that leaves me with, actually, let's factor out negative cosecant, because there's a negative right here, right? Okay, so that leaves me with sine v. Okay, if we factored out negative cosecant, this whole one is gone. So we've got minus cosine v cotangent v all over cosecant v, and that's cosecant squared v. Okay. All right, we might try to clean this up a little bit more. Um, Yep, we can cancel out a cosecant here with 1 from our denominator. And I'd be interested, I might leave it alone. Cotangent is cosine over sine. So that's not going to cancel anything out. So let's just leave it at that. Yeah, I still have my little negative. So we get negative sine v minus cosine v cotangent v over cosecant v. All right, questions about that? Yes.
If you pull the negative cosecant out, would it not be minus cosine v cotangent?
Yep, I left it as minus.
Would not be plus?
Well, there was a minus here, and then there was minus here. I took this entire minus cosecant v out, so that wouldn't change this. We factored out a minus. Okay. All right, other questions? Okay. All right, why don't you try D on your own? Okay, try D on your own.
Is the 8 theta part of the cosine?
It is cosine of 8 theta, and then all of that squared.
So 2 goes to everything.
Yes. When we put it on the trig function, then that means it's to everything. Really, when it's on the trig function, that exponent is really on the outside. It's on the, yeah, outer part. This is really cosine 8 theta squared. Okay, the square is on the cosine. So in this one, I'm going to bring that out front first. So we get 2 cosine 8 theta. Okay, so my most outer part is that squared. Okay, now I come on the inside and I have to take the derivative of cosine. The derivative of cosine, I'm going to do this just for clarity, is minus sine 8 theta. Okay, I just take it one layer at a time. Don't change that 8 theta yet. Now I'm at this part. The derivative of 8 theta is what? 8. Okay, so that's our derivative. Okay. Okay, question?
Why wouldn't you write it like I read it wrong, so I did it wrong. I wrote cosine and then I put the 2 to 8 in the theta.
That's just not our notation. When we have a trig function raised to a power, the whole thing, we put the power on.
But like the other one earlier, I was trying to do that and I wasn't supposed to. You know what I'm saying?
Let's see. Let's go back.
Problem. Right there. See the top?
Well, in this, you're talking about this one, right?
Yeah, I'm just confused at where to.
So I was saying that this and this are different. Okay, here the square really was on the argument. right? Versus in this one, the square is on the function. And this one means this thing. The square right here indicates that the whole thing was squared.
And that's what we just did.
That's what we just did.
The squares on the function.
Right. Versus the square on the argument is there.
Mixing up.
Okay. All right, other questions about that before we simplify a little bit? Yes. Okay. All right, so if I'm going to simplify, I would get negative 16 cosine 8 theta sine 8 theta. Okay. And using some of our trig functions, we might even see a different simplification of that. We could use the double angle formula. And I don't know. I mean, I'm just trying to prepare you for whatever you might see, especially in, I don't know, hopefully if you did this on the test, I'd be thrilled. Okay, so let's just leave it at that. All right. All right. Questions about this? All righty. Okay, what about E? All right, y equals 3x minus 5 cosine pi x squared. Okay, so let's first of all kind of analyze our problem. What do you note about the structure of our problem? What kind of rules do you think we're going to use? Product? The exponent rule. Okay, we'll be using our power rule at some point.
I don't get what to do with the 3x minus 5.
Okay, well, wait. The 3x minus 5 is not really a thing. There's a 3x, and then there's this. So we've got two terms. So what we would do is take the derivative of each term, Yeah, that's just our sum difference rule, right? So that's what we're going to do there. So the 3x is really not a problem. Okay, so the derivative of 3x is just what? Okay, got that part. Now I need to deal with minus 5 cosine pi x squared. The square is on pi x. So the minus 5 is just a constant multiple. All right, so once I take the derivative of cosine, yes. Okay, so, and in this case, cosine is on the outside, right? Because that square is on this thing. It's not on the argument. Very good. It's not on the function. So the next piece then, the next layer of this is the derivative of cosine. It's minus sine pi x squared. Now I need to deal with the what? The exponent. Very good. Okay. The square is right here. So we do 2 pi x. Okay. And then finally, we deal with what? Pi x is just pi. Okay. Questions about this?
So, this sign is different from the previous one we did because it's not parentheses all around. For a 3x, you treat everything on one as individual.
Right, it's just a separate term. So we had, we've dealt with that before. If we had y equals, let's say, 3x squared plus 2x minus 7, we take the derivative of each of these terms. So here was a term, here was another term. We take the derivative of each term. This is the derivative of 3x. All of this is the derivative of 5 cosine pi x squared.
Yeah, because all of it wasn't all squared.
That's right. Yes.
Possibly for the phi part, could you break down the f and the g prime and
Okay.
correlate which parts go to which?
All right. I'm going to try to write it. Okay. Of course, we had the 5. And then I said our outer layer was cosine. Okay. Cosine of what? We had something squared, right? As far as I'm writing it in order of the layers. I don't know if this is helping or not. But cosine's on the outside. Then we had the square. Then we had the pi x. So my most outer part is cosine. And then I took the derivative of cosine right here. Okay, not changing anything that was on the inside of that. Okay, then my next piece is the power. So this is where I took the derivative of the power. Okay, we got a 1 left right there. And then finally, we dealt with the inside. And so here's the derivative of that inside. Okay, does that help? All right, other questions?
So how do you simplify that?
Okay, um, I'd say it's probably not so bad. Okay, the 3 is just 3 minus 5. He's up front. And actually, notice that this really is a big giant product, right? Okay, so I've got minus here and minus here, so this is going to become what? Plus. Okay, and I guess, I could go ahead and put all my constant multiples together. I actually have what? 5 times 2 times pi, right? 5 times 2 times pi. So this is really going to be 10 pi plus 10 pi sine pi x squared. Actually, there's also this one. So that would be what? Pi squared, and then there's an x. Okay? Remember that sign, he could not be separated from this thing. So they're a package deal. We can't break them up. All right? They stay there together. And I guess that really kind of happened up in here. They stay together. But notice we got pi times x times pi times 2 times 5 and times a negative. Those are all the things we multiplied together. 2 times 5 is 10. I got pi times this pi over here times that. Wait.
Would it make it easier if we just multiplied it out first?
Multiply it out first?
Yeah, like multiply the negative 5 to each of them.
No, no, no. You don't multiply them
But
to
I'm
each
saying
other.
do that and then take all the stuff out. That would make it easier.
Well, when you say multiply them to each other,
Distribute those terms that you're supposed
there's no reason to distribute because we only distribute over a sum or a difference. We don't have, in all of this right here, there is no sum or difference. It's 5 times negative this thing. We're not adding or subtracting. Times this times this. Yes.
So what allows us to take the negative off the side within what can't be multiplied to?
The negative is out front of the sign. Right. So negative 5 times negative becomes positive.
And your -1 right there.
Okay, y'all keep saying, where's the negative 1?
Imagine from the sun.
Oh, yeah, okay, yes. Negative 1 is here. We can say that. Okay. All right. Back to you, Preston. No, you okay? All of it, like we've got, I would say we have 1, 2, 3, if we count these individually, 4, 5, 6 factors here. But we don't have any addition or subtraction here. So when we say, A times B times C, that's not A times B and A times C. We don't distribute over a product like that. Okay, we just smush everybody together. So I've kind of brought together all of my constants, constant multiples, I should say. So here was a constant multiple. The negative was a constant. The 2, the pi, the pi. So when I put all those pieces together, 5 times 2 gives me 10. The negative with the minus made it positive. Pi and pi gives me pi squared. And the x I wrote at the end. I could have put it over there. Okay, and then what was left was sine pi x squared. Okay. Questions about that? All right, very good. F could be a beast, but I guess we should try it. Let's see where we're going after this. All right, let's tackle it. We're not afraid. All right, first we need to try to get an understanding of it. So I've got cosine, okay, well, let's just rewrite it first. Y equal. Okay.
I was about to ask, is tangent part of sine's argument?
Yes.
Wow.
Yeah, we've got tangent. We're taking sine of tangent pi x. Yes. I don't see any products in here because we have to have cosine of something, right? And then we got to have sine of something. Okay. All right. So I'm just rewriting cosine of. We're not going to have a product. What are we going to have that we're going to have to deal with? A power. Cosine of sine of tangent pi x to the 1/2. Okay, so we just rewrote it with our exponent. Okay, the most outer layer is what? Cosine. Do I need to let them or tell them to let you bring highlighters to the test? Because if I don't say it, they won't let you have it. The which part? No, cosine is on the outermost. We're taking cosine of, and the 1/2 is part of the of. Okay? So cosine is on the outermost layer. Then from there, what's next? Nope. What is it? The 1/2. Got to deal with that. Okay. Is that what you said? Okay. Then what? Then the sine. So let's do some tiger orange. Okay. Then tangent. Oops. Used that color already. Running out of colors. And then finally, pi x. Okay. So one layer at a time. Okay. So I'm going to start over here. Y prime equals, well, the derivative of cosine is negative sine. And I don't change anything on the inside. Okay. So negative sine of sine tangent pi x to the 1/2. Okay, we're going to need lots of space. Okay, dealt with that piece. Now I'm going to deal with the 1/2 piece. So times 1/2 of sine of tangent pi x raised to the what? Raised to the negative 1/2. Okay. Next layer is what? Sine. So the derivative of sine is cosine. Okay. And the inside part stays the same. Okay. Now we need the derivative of tangent, right? So the derivative of tangent is secant squared. Is that right? Of pi x. And then finally, the derivative of pi x is what? Pi. Okay. And just leave it like that. For the most part, that's what I plan to do because it's not like those are inverse functions. So, yeah, I don't think there's a whole bunch of simplifying we're going to do with this. These two look like they might be alike, but let's see. Um, except I can't separate this from this thing, right? It's sine of this. So I cannot cancel those two out. Do you see that? Sine can't stand there by itself. It has to be sine of something. So it's married. They're tied together. Okay. All right. So we can't separate those out. So I think I can bring out pi over 2. Here's a 1/2. Here's a pi. I'm not even going to rewrite it. Okay. The only thing I would do differently is minus pi over 2. I could put this whole thing in my denominator, so I will rewrite it. Okay, so we're going to say minus pi, okay, because the minus here, the pi there at the end. We've got sine of tangent of pi x
You can't get rid of the 1/2 too.
to the 1/2. This 1/2 right here?
Yeah.
Yeah, he's going to be in my denominator. Okay. And then this whole thing is going to be in the denominator. So sine of tangent pi x that's to the positive 1/2. And then cosine of tangent pi x. And then secant squared of pi x. Okay, I think we got it all. Okay, questions about that? What? Right here? Okay, where did it come from? One, two, three. Gotcha. Let's see. That's him. Then is. No, it's important. And I tell you what, if you ever get into some programming and you leave that parenthesis out, you'll find out how important it is. It could ruin your day. So we want to make sure we put all that stuff in there. Okay. Other questions?
Is this about as far as it gets?
Which part?
Whole part.
The whole part, like the whole class?
Well, for this, then you pretty much have to.
You know, we're getting there. We're getting pretty close. Okay. All right. Okay. Need some more of that? Where is it? There. What we do know from this is we've got to know those trig derivatives. Okay, so if you don't know those, go ahead and know them. Put them on some flashcards, take pictures of them, flip through them on your phone. Okay, um, and then we got to know all of the derivative rules, and now we have to know how to use the derivative rules with one another, with each other. Okay, all right. Okay. All right, so find and evaluate the derivative of the function at the given point. So this kind of goes back to some things that we were doing before. Now, though, we just know how to take or how to apply the chain rule. Okay, so, well, no, I'm just saying the only thing that's new to this is the chain rule. But otherwise, we've evaluated the derivative at a point before.
With these problems compared to the other ones that we did before that looked like this, do you have to do the chain rule with this one?
I would say yes. You have to use the chain rule. Okay. Very good point. All right, so I'm going to rewrite this first. We have y equals 3x cubed plus 4x raised to the 1/5. Okay. All right, so the derivative, bring the 1/5 out front. 3x cubed plus 4x. Okay. If I subtract 1, I get what? Minus 4/5. Okay, so my outside, I didn't highlight it, but um, the outside is the power, right? So we dealt with that. Inside stayed the same while we did that. Okay, now I take the derivative of the inside, and so we get 9x plus 4. And now that feels like a piece of cake, right? Compared to where we could go with this. Okay, so there's my derivative. All right, if I wanted to, I can clean that up a little bit by saying 9x squared plus 4 over 5 times 3x cubed plus 4x to the positive 4/5. Okay, and they want us to evaluate this at the point 2, 2. Okay. Okay, so what I'm going to do is plug in 2 wherever I have x. That's all. Okay, so 9 times 2 squared plus 4 over 5 times 3 times 2 cubed plus 4 times 2 to the 4/5. Okay, 36 plus 4 is 40, right? Nope. Yeah. And then we've got, okay, 32 to the 4/5 is going to be what? 16? These twos? I mean, you got to say, you don't have to. So if I do just the denominator, it's going to be 3 times 2 cubed, okay, plus 8, right? Plus 4 times 2, or 8. Okay, and we're going to raise that to the 4/5. How did I get 2 parentheses there? Okay, they gave me those. Okay. 16.
Times 5.
Okay, well, I still got to multiply by 5, so that's 80. Multiplying 16 by 5 is 80. Okay, we get 1/2. Way over in the by and by. Okay, we made it. All right, so that was that. The hardest part of that was plugging in. Can you believe it? Questions about this? Okay, good. All right, this time they want us to additionally find the equation of the tangent line. Okay, this problem looks a little like the last one. What's different about it? Okay, we got a product this time, right? Okay, and I'm not just talking about the 1/3, because if there was just the 1/3, that wouldn't be a problem. That's a constant multiple. But we've got that x out front, so that's going to force us to have to use the product rule. Okay, so let's see if we can do that. First, I've got to find the derivative. So f prime of x. Okay, I'm just going to pull the 1/3 out. He's going to go along for the ride. My first is going to be x, and my second is going to be all of this, which I could rewrite as 1/3 times x squared plus 5 to the 1/2. Okay, so we got 1/3, and my first is going to be x times the derivative of the second. I'm going to deal with that in a minute. Plus the second times the derivative of the first, which is just what? 1. Very good. Okay. All right. So what's the derivative of the second? Okay, this is my second. 1/2. Is that it? Times 2x. Got to go inside and take the derivative of the inside. Times 2x. Okay, that's my derivative. Questions about that? Okay. Okay, so I use the product rule, right? I got away from my colors over here, so let me rewrite this a little bit. We had 1/3 times x squared plus 5 to the 1/2. Okay, so we decided that we would let the 1/3 just kind of be constant multiple. That's why he's out here. And then x is going to be my first, because we're going to use the product rule. And then this is my second, where we'll have to use a chain rule. Okay, so we get the first times the derivative of the second. All of this is the derivative of the second. Okay, plus the second, this is actually the second, times the derivative of the first. So we used a product rule. Okay. All right, and then that was our outer kind of piece. But then to take the derivative of the second, I had to use the chain rule. All right, so that's when I brought the 1/2 out front. I subtracted 1 from my exponent, and then we take the derivative of the inside. Okay. And so now we need to clean this up a little bit. I've got a 2 here. I can cancel it with that. Okay. I think that's all we can do preliminary wise. So I can factor out what? Can we factor out x?
I'll
Uh-uh.
go ahead and combine those x's before you
It's on
take
x
something
squared,
out.
wouldn't it be?
All right, you want me to go ahead and combine the x's? Okay. All right, so we got 1/3. Then this is going to be x squared times x squared plus 5 to the negative 1/2 plus x squared plus 5 to the positive 1/2. Okay.
Factor out x squared plus 5.
To what power?
Negative x 1.
Okay, factor out x squared plus 5 to the negative 1/2. Okay. So now, oops, I'm sorry, got too excited. Sorry. He's not out there. Okay. All right, so now what's left?
X squared times
Very good. X squared,
x squared plus 5 to
not times. This is a
plus what?
plus, right? You factored out x squared plus 5 to the negative 1/2. He's out. So we're left with x squared plus what? That's right, to the first power. Okay. Questions about that? So this cleans up as my numerator is going to be 2x squared plus 5. And my denominator is 3 times x squared plus 5 to the 1/2. Okay,
Get your explanation as to how it became just a 1 for x squared plus 5
right here.
within the brackets, yes.
Okay, so we were able to factor out x squared plus 5 to the lowest power. The lowest power was negative 1/2 between these two. So then what I do is I subtract my exponents. 1/2 minus negative 1/2 is going to give me 1 right here.
But we're multiplying that back in.
When we multiply it back in, the rule is we add the exponents. So minus 1/2 plus 1 would give me positive 1/2. Okay. All right, other questions?
Where did the 2 come from in the numerator?
We had 2 x squares right here.
Okay.
All right. So what they wanted us to do was find the equation of the tangent line. So what do I do next? Okay, plug in 2. That's going to give me my what? My slope. Okay, so my slope at the point, they said it was the point 22. I hope that's right. 2 times 2 squared plus 5 over 3 times 2 squared plus 5 to the 1/2. Okay, so we got 4 times 2 is 8 plus 5 is 13. That's 9. 1 to the 1/2, which is 3 to the 9. Okay, that's my slope. All right. And now what do I do to get the equation of the line? Point slope formula. Y minus y1 equals m times x minus x1. Okay, y minus 2 equals 13 ninths times x minus 2. Okay, and so we get 13 ninths x minus 26 ninths plus 2. Okay, or 13 ninths x. 2 is going to be how many ninths? 18 ninths. So negative 26 plus 18 is going to be negative 8 minus 8 ninths. Okay. Questions about this? Yes, because you're going to be great. Well, in this case, I mean, for an equation of line, it's standard to write it in y
No,
equals.
not the, I'm talking about when you plug in to find the slope. Can we just, like, because after you find the derivative, I don't see why you would simplify further than that if you're just plugging in the numerator.
It's just a nice, neat package. I mean, no, you're absolutely right. You don't have to. But there will come a time when, maybe we want to set that equation equal to 0, and that's when we want to have it in this nice factored form. So, yeah, we could have skipped that. But it's good practice for what's coming. Okay,
Could you show the,
final.
slope formula?
Okay, questions about that? This is where we start at. Okay. Okay, questions? Okay. All right. Okay, find the second derivative. That sounds like it should be easy. Oh, yes, okay. All right, so let's do that, and maybe we'll stop there and talk about what we're going to do next. All right, see what you can do with this on your own. Okay, f prime of x. Well, first of all, we need to make sure we understand that this is secant pi x, and it's the secant that's squared, right? Okay, so the square's on the outside of secant. So then we get 2 secant pi x. And if we had, we can write it like that to the 1. We don't need to do that, but for clarity. Now I'm going to take the derivative of secant, which is secant pi x cosecant pi x. And then now we take the derivative of pi x, which is just pi. So I'm going to sneak him up here so I don't have to rewrite it. 2 pi times secant pi x. Oh, yes, I'm sorry. Sorry. I got too excited. Okay, how many people were able to get that? Okay, good. All right, very good. Okay, there's a little pi right here. Okay, so this puts us in a pretty good spot. Okay, we can combine them. Now, what were you saying? But what?
Aren't they married, the first one?
They are married, but this is. I'm so glad he said that. This right here is another way to write this. Okay, this is equal to secant pi x times secant pi x. That's what it means for the whole thing to be squared. So, yes, he's absolutely right. We could write this as 2 pi secant squared pi x times tangent pi x. Do I have to take the derivative again? Oh, I thought we were done. Okay. So yes. Okay, we got to take the second derivative.
So then let's not combine with them.
Well, no, I think it's best because otherwise we've got a product rule that has 3 different pieces. And that would be, we hadn't even talked about what to do with that. So let's do it. The good news is 2 pi is a what? Constant multiple. So 2 pi is just going to go along for the ride. and I'm going to use the product rule on this. Okay? Well, let me do it like that. All right. So if I do my first, okay, times the derivative of the second, well, the derivative of tangent pi x, we just said was, no, it's actually secant squared pi x. First times the derivative of the second times what? Well, are we done with the derivative of the second? Let's come back to it. Let's come back to it in just a second. So we got first times the derivative of the second plus the second times the derivative of the first. Okay? So let's look at the derivative of the second. Okay, the derivative, what's that? Yeah, the derivative of tangent is secant squared, but then when I go on the inside, I still have to multiply that by pi. Right? And then, so here's our second. We need to do the derivative of the first. For this, we're going to do what? Two secant pi x. That part was our power rule. We're going to need some more space. Okay. All right, so that right here, because I'm having to use a power rule. It was secant squared, so I brought my 2 down front. Pi.
What we had before, what we did 2 pi secant squared pi x the entire.
You got to show it to me.
The first derivative that we found would be what we would put in right now. Because it's the secant squared pi x. Is that what we're finding the derivative of?
First times root of the second plus second time. Okay, yeah, we could be smart like that. So yeah, we could save ourselves a lot of trouble, you're saying, by just putting all of this. Okay. I like that plan. So we're doing first times the derivative of the second plus second times the derivative of the first. Well, notice that what we're calling the first is what we started with. So instead of going through all these steps again, we can think smart and say, hey, let's just pop all of this in here, because we already found the derivative of secant squared pi x one time today. Right? We started with that. Now, you don't have to do that. We could go through all these steps again. We'd have to write all of this out and then eventually simplify it down to this. Okay, but we decided to try to be smart. That was very, very smart. Okay, so we get 2 pi secant squared pi x times tangent pi x. Okay, from the previous work. And then we can go back in here and try to clean this up. Okay, what kinds of things do we have in common? Because I got 2 giant terms. Here's one, here's the other. So we got secant squared pi x in both of them, so I can factor that out. That's going to leave me with secant squared pi x here. Okay, and then plus 10 pi x. Okay, so we are trying to clean this up. Yep, okay. I think I can see the whole thing here. And we've got the 2 big terms that we've already outlined. And so in these two terms, they have secant squared pi x in common. Okay, I've actually got secant to the fourth over here, right? But I hadn't even multiplied them together yet. So I'm just going to factor out secant squared pi x. So that's going to give me 2 pi secant squared pi x. Okay, I think that's all that I see in common. And then I'm left in this first term with pi secant squared pi x. Right? There's my pi, and here's the other secant squared. Here's the pi, the other secant squared pi x. Doesn't matter which one we factor out, I just happen to underline this one. And then over here, okay, we factored out secant squared pi x. I'm left with, there is a pi over there that we could have factored out. But I'm left with 2 pi and tangent squared pi x. And yeah, that's it. If I wanted to go one step farther, I could factor out pi's. And so we would end up with 2 pi squared secant squared pi x, okay, times secant squared pi x plus 2 tangent squared pi x. And that's the end of it. Okay, what do y'all think?
So they're not married in this one.
They're always married. So there's no place where, when I say they're married, there's no place where I separated secant from pi x.
Okay, the argument.
Right.
Think of it like they just share a partner. They're married, but they share a similar partner, which would be that pi. That's why you can just take
Which
it
pi?
out.
This pi right here?
Yeah, that's why you
Yeah,
can take it out.
because that's not part of it. I mean, the marriage is right here.
Right. See, I was looking at. Yeah, you're right. You never separated their marriage, but I was looking at like this. I was looking at this is like the marriage.
No,
Where,
no, no.
like, this is part of that, which is not.
Yeah, it's secant. I mean, you can't just say secant. It has to be secant of something.
Right. That's where I was getting.
Right. So, I mean, sometimes people want to say, well, we can factor out this pi right here. No, you can't, because it's tied to secant.
But like earlier, the problem F that we had, they did use actual tangent for the thing. Like, see where you circled it in green?
Uh-huh.
That was marriage or whatever. You know what I'm saying? Like they actually did. This was all part of it, right?
Right.
It was the argument.
Right, yeah, because those were just they were really intertangled.
Right,
I mean, it was
that's correct.
tangent of that, but then sine of what? Well, it's sine of all of that. And then what's this sine of? Well, it's all of that.
Right.
So, yeah.
But so like if the problem wants to, it can actually put a trig function and argue.
Yes, yes. Okay. All right, so I'm going to say we're done with that one. All right, in this problem, just a word problem, what we need to do is determine the position and velocity of the object when t equals pi over 8. And this is an object in harmonic motion, which we talk a little bit about in trig. When we have an object in harmonic motion, it's going back and forth, okay, up and down or something like that, kind of like a spring. This is my position function. So if I'm trying to determine the position when time is equal to pi over 8, then the only thing I need to do is plug in pi over 8. Okay, I know it's the position function because it tells me that this is the displacement. right? So displacement is, a way that we can measure the position, all right? Y is measured in feet. So we're going to say y equals 1/3 cosine 12 times pi over 8 minus 1/4 sine of 12 times pi over 8. And we're just plugging in this one, so we just got to go through and evaluate this. And we've got cosine of 12 over 8 is going to be 3 pi over 2. 12 over 8 is 3/2, so we get 3 pi over 2, okay, minus 1/4 sine of 3 pi over 2. Okay, well, one of those, or 3 pi over 2, is actually one of our quadrantal angles. That's at how many degrees? 270 degrees. Okay, so we know that cosine of 270 degrees is what? 0. Okay, so this whole thing is going to be 1/3 times 0, and then sine of 3 pi over 2 is -1. So we get positive 1/4 feet. Okay, so at time equals pi over 8 seconds, the spring is at a position of 1/4 of a foot, 1/4 of a foot. Okay, so now if we talk about the velocity, in order for me to get the velocity, I've got to take the derivative of this position function. So we get y prime equals 1/3. The 1/3 is just a constant multiple. And it's going to be cosine of 12t. I'm sorry. Okay, 1/3 is the constant multiple. The derivative of cosine is negative sine of 12t. And then the derivative of 12t is 12. Okay? All right, so we took the derivative of our first term. Now we say minus 1/4 is a constant multiple. The derivative of sine is cosine of 12t. And then the derivative of 12t again is 12. And so we can clean this up a little bit. Okay, 1/3 times 12 is 4, plus we have this negative sign, so I get negative 4 sine 12t minus 3 cosine 12t. Okay? And so the derivative, or when we evaluate this at t over 8, we get minus 4 sine 12 times, or rather it's pi over 8 minus 3 cosine of 12 times pi over 8. So again, 12 times pi over 8 is 3 pi over 2. Okay, we already said that cosine of 3 pi over 2 is 0, so this whole piece over here is going to be 0. And then sine of 3 pi over 2 is -1. So -4 times -1 gives us 4. And this would be feet per second, okay, for our velocity.